I wanted to make a little video here about this setup. There's a lot more going on here than seems to be obvious. Right now in the beginning here on this, I put this in the program just to prepare the setup material, the aluminum setup material with this deep hole that's in there, because the stock that I'm getting, let me hide the steady rest, let me hide everything but what we need to see here. The stock that I'm getting already has this 1.4 inch hole. I kind of mentioned this in a previous video on making the this piece that's going to go in this hole that I'm going to drill into, which you'll see a little bit later in this simulation. But there's kind of a lot of things going on here, and you have to make the right order of sequences to get this done. So that was just to drill the hole in the setup material. And now this is going to be the actual beginning of the machine work that's going to happen. So here's the rough turning OD. There's a thread, kind of a pin end thread on the end of this part, and this is just roughing down here. It's taking kind of shallow cuts, you might notice, because there's actually holes that this tool is going to be intersecting, and it I wish I could get rid of these. See these icons that come up for the speed of the simulation? If anybody that's working for Esprit sees this, let me know how I could get rid of those little pop-up things. But anyway, and that's the finish OD tool. It's going to finish it roughs the thread relief, and then it finishes out the OD for that end. Now this is just going to spot drill for some holes that start the gun drills that go in here. That's milling one of them to size. And this is a 218 diameter gun drill that goes deeper down in the part below the ports that are going to be put in the end of here. And one of the reasons I want to show you this simulation is the importance of the order of operations in a setup like this, because if you do certain things before other things, you wouldn't be able to accomplish the machine work, is the only way I can kind of put it. So in particular, this hole that it's drilling right now, there's these pins that go in the bore here, and they get halfway machined away. So that's the initial reaming of those holes, just so I could start the reamer further down here. You'll see in a second what I mean. So this is a feed mill, 1.5-inch diameter Mitsubishi feed mill, actually, is what I'm going to do this with. So it's going to rough down that. Let me pause the simulation right here a little bit. It roughs the initial counter bore, and this bore has a counter bore, and then it gets a little bit smaller up in here. And if I play this a little bit more, you'll see what I'm talking about. See why I had to drill those holes first, because it's going to machine away, but I have to leave stock here, if you see this hole, so that I can finish reaming it. And the only reason I didn't ream it all at one go is my reamer's just not long enough to reach down in there. The shank of the tool had to be relieved even to get from the point here down. But if I went in and machined the bore out to size at this moment with this feed mill, it would be cutting halfway into this hole, and I wouldn't be able to finish it to size. So what I'm doing is I'm roughing it out up to the hole here, down to almost the finished depth, and then I'm going to come back after that and finish reaming those holes. But like I said, the reamer that I have, or the reaming tool, well, this is just a boring tool to bore it out a little bit more there, and this is the reamer. Pause the simulation here, let me slow it down a little bit, and it's going to ream down to depth, as you see there, the depth necessary. But if I was to have roughed out that material, the reamer would there would only be half the hole left, as you're going to see in a second here, because the roughing end mill is going to rough that out after this. So then we come back with the feed mill again, and if I let it run a little bit here and then pause it, you'll see what I'm, let's see if I can pause it here. You see how this is cutting half that hole away, because what they do is they put pins in this bore, and it must index something, and half the pin projects into the bore, and the only way to get that hole in there is to drill it before you rough the bore out. Well, I have actually milled them from the side, like with a 5-axis move, but that's kind of a pain. I'm just going to try to do it this way on this part. The only disadvantage to doing this is it gives you a little bit of an intermittent cut on the finished boring tool, but I don't think it's going to be too much of a problem, and this titanium's pretty soft. That might give you more of a problem in something like Inconel or something like that than this material. So let me kind of speed this up a little bit more. Yeah, this software has this window that comes up here. If I move the mouse away and back, see that little pop-up window about feed override? I wish there was a way I could turn that off for these video simulations. So that's the feed mill roughing down now the bore to full size almost. And then this is just going to be a heli mill, ISCAR heli mill, to finish the bottom face. And the only reason I'm doing this is because I don't want to put a small enough boring bar in to face down to the middle. So this is the, maybe I could just cut this away, you could kind of see this better. This is the roughing boring of the remaining smaller counterbore below. It already roughed this one above, and then it's going to do a finish cut down the whole bore. So that's the finished boring cut. And then let me see, I can't remember what tool comes next now. Oh, this is a little, I don't know if you remember the last video I made, there was this little drilling fixture thing, and this is the part that's going to mount in the part to hold the other piece down in that hole to drill. You'll see that a little bit later in this simulation. So everything kind of has to be done in the same order. You notice on this new Esprit simulation how you can put the actual models of the tool holders. If I turned on well, let me not turn on that, but I'll turn on the spindle of the machine. You can see the spindle of the machine here, but it's clearer without that. So for right now, this is just taking this is a 5/16 end mill. It roughed it out with a 1/2 inch end mill, and then this is the heli mill again to rough this bore. Now this is an issue here that I have to be very careful with, because this bore gets roughed. I'm going to pause it right now for a second and get up a little closer here. The first part of this hole, maybe I should look at it from the side a little bit more here. The first part of this hole here is got a close tolerance and finish, but the back part of the hole, for some reason the engineer designed it with a 38mm bore, or hole, drilled hole if you will, but the hole in the front is only 1.501 plus or minus 1/1000th tolerance, and it has to have a 32 finish that goes back in here. You'll see that in a second when it finish bores it. But if I was just to drill this with drills, 38mm is 1.496, and the finished bore in the front here is 1.501 plus or minus 1. And if I put any kind of little scratch or anything in the front of this bore, it would pretty much screw the part up. So I need to be very careful here. What I'm doing is I'm going to rough this out down beyond that bore, and then we're going to come in with the boring head and bore it to size to the 1.496 diameter of the drill. So that's what that's doing there. And then I'm going to come in with the short drill. I got to do this with 2 drills because it's such a deep hole. And what I'm going to do is feed into that hole with the drill running backwards to where I get beyond where this good finish has to be, so I make sure I don't scratch it or put a gouge in it, that because I'm only going to be boring out about 5 or 6 more thousandths of an inch off that, which is only 3 thousandths on the radius on the wall. And so I can't afford to put any scratches that are too deep in there. So this drill, this spade drill, it's going to be is I'm going to run it in reverse at a low RPM till I get back into here like you see it, and then I'm going to drill down to depth, and I'm going to basically do that with all of the tools that go down into this hole. So this is the short drill, and you may have seen these drills on the Instagram post that I showed, and then this is the longer drill that's going to go all the way to the bottom, which is 20 and a 16th of an inch, 20.06 inches from the face of the part to the bottom of this hole. And then the bottom has to be flat bottomed with a 0.190 radius on the corners of the flat bottom. So that's what this drill is doing right there. So that's the drills. And like I say, I have to be very careful of the front of this bore right here, kind of where the mouse is, not to scratch it or gouge it too much to where it won't clean up to the inch 1.501 diameter. So that's important. And these are the 2 screws that I talked about in the previous video that's going to hold that drill fixture in. Now there's the boring head to bore it to size. So that's how deep the 1.5 inch diameter goes into there. These little marks here you see are the simulation. If I increase the resolution in the simulation, you probably wouldn't see that, but it takes longer for the computer to handle it. So that drill fixture thing that I made in the earlier video is going to fit in this triangular kind of pocket, and it's going to hold that piece, the sacrificial piece, way up here at the other end of the bore, or hole if you will, so that I can drill these cross holes, which you're going to see later in this simulation. So let's just continue to play it. This is the OD thread, and then the blunt start. Let me make this more solid so you can see this blunt start a little better. And this is now I've had a lot of people ask me about blunt starts in the comments, or a Higbee blunt start, whatever you want to call it. Now you can see it's milling it here. And this is the way I typically do it on the Integrex, because I like the way it looks. I like the way this finishes the blunt start. This thread in the simulation will probably be a little bit deeper in reality. That's why you see this little bit of a step in the blunt start, because I don't think I've gone to depth in the simulation on that thread. I think it'll go a little bit deeper. I went to the kind of the minimum depth on the Acme thread according to the gauge maker information, and I usually adjust that with the offset on the machine when I thread it. But this is basically, there's a couple different ways to make a Higbee or a blunt start, and the way I do it on the mill is I just draw a helix, and I profile down that helix that matches the pitch of the thread, of course, and the way you can line this up is using a different fixture offset, and you use your C-axis fixture offset to line it up. So I usually start the blunt start helix right at Z0, and I feed in with cutter comp, and then I go around the helix. In this case, it's rotating the C-axis to make it, because I can't go below X0 too far on this machine, so I have to do it that way. If you had a machine that could go further around, you could just mill it down around there. But this Integrex only lets me go 10 millimeters X minus, and then it hits the limit of travel. So I have to do everything above and do a rotary milling type of thing. But basically it's the same thing. It's just a different style of milling. And what I was saying is, what I usually do is, you see where the thread just kind of angles out to nothing on the end of the part, and it's pretty easy to line this up. If what you do is you program that helix, you don't worry too much about the alignment of it in the simulation, although it actually looks pretty good here, but it wouldn't matter because you can adjust it when you run it on the machine. So what you do is you let it come in single block until it's right at the beginning of that helix, and then you stop the machine and you look at it and say, am I in a line with the beginning of that thread or not? Right where the last scratch of the thread comes out the face of the part. And if you're not, you kind of estimate the amount of angular displacement or rotation that you're off, and then you adjust your C-axis fixture offset that you're running this on. You run it on a separate fixture offset, and you adjust the C0 of the offset until you get it to line up when the tool first comes in here, and then it'll go around and it'll be in a line. Now, an Acme thread has a flat on the bottom of the thread, and it's pretty easy to line up an Acme thread. But if it's a V thread, you can then, once you get your sort of rotation in the right place, you like it, then you can stand off with your Z offset on your tool until you keep moving it in and keep rerunning the Higby until you get it lined up with the bottom of the V of a V thread, and then use your diameter offset because you're using cutter comp here. If you programmed it that way, you can adjust it till it gets down to the depth of the thread. If it's not that far, if it's off a little bit there, you can start with the cutter bigger and then move smaller until you get it lined up, which is what I'll do in this case as well. So that's the way that I like to do a blunt start, and I like it also because I like the shape of it here rather than using a grooving tool. Now the other way is with a grooving tool on a lathe that has no milling, and you program a very short threading cycle just like the one that makes the longer thread, and you pull the tool out after you get maybe one lead of the thread in. You retract the tool, or you make it only that long, if you will, and depending on the RPM you're running and how fast the rapid movement of your machine is, it depends on how far it carries this around, but it tends to make it more like that gray color you see there when you do it with a grooving tool, and I don't like the shape of that as well. So that's the couple ways, different ways to make a blunt start, and you do it the same on the ID as the OD. There's no difference really, except that you kind of have to conventional mill it on an ID thread, but that's really not a problem with this. It's such a little amount of material you're taking away. So that's the blunt start. Let me go back to a semi-transparent view, and we can see the rest of this. So the next thing is a chamfer on the bottom of that, or on the front of that bore, that close tolerance bore, and that also has to have a 32 finish on it. So I'm just doing that with a separate tool. Let's see what, I can't remember what's now. Oh, these are the port tools. So this is just a drill to rough the ports out to size. Well, or not to size, but just to get the major meat of material out of there. And then there's a rough porting tool, which is this tool. Going to feed in to rough the port and get that little counter bore in the bottom roughed out. And I posted an Instagram post showing some tools that I was setting up for this, and I showed these in the picture, the real tools. And then here's the finished port tool. And I found that I have to feed this up and back. I don't like to do that with tools too much, but in this case, if you just wrap it out of that hole, it leaves kind of a spiral mark in the hole, and they don't like that because this finish has to be good on this port. Some kind of O-ring seals or something in there. And so then there's a snap ring groove here, which I ground a special tool for. And then there's these spanner wrench holes in the OD of the part on this end. And so then we come up to these holes up here, which is what I made that drilling fixture for earlier. I don't have the fixture modeled in this model, but you can kind of get an idea what it's going to do. It's a spot drill, so that this drill doesn't wander off too much. And I drilled part way down so that I can start milling these counter bores, because my drill's just not long enough. I couldn't find the right length drill, and now I drilled a depth with that drill, and I was just a little beyond the flute length. So then I resized there's a thread that's going to go in here, and I have to size that hole and let me pause this a little bit and mill this chamfer in the beginning of the thread they specify. And here's a 5/16 24 thread mill. Let me slow this down a little bit so you can see this. Oop, a little bit more maybe. So this is a thread milling cycle, and that's one of those thread mills with just 3 teeth on it out on the end. And we come back on and bore these holes to size with the boring head. I'll probably really use a bore orient retract cycle, but on this simulation it'll show a collision with the boring bar if you actually put it in the program here for some reason. And then a chamfer on the top of those 2 bores. There must be a plug with some seals that's going in there to seal off. I think they put some kind of pin. You can kind of see the reason that I needed that plug to support the drill now. So you see how the drill is almost totally in the hole itself, and you would never be able to drill a hole like this. It would just deflect into either to break the drill or mess up the bottom of this hole down here, by deflecting the drill. And it might be possible, some people in the comments on that video on this device suggested doing some kind of a end mill down in there, but this is a 1/4 inch diameter hole, and that's an awfully long end mill to reach down beyond this threaded part and mill all the way down to here, and it would be just very difficult to do, if even possible at all. So that's everything there. Now here I'll get a collision with the steady rest. It actually shows it in this software, but this isn't the way my steady rest. Right there it collides with the steady rest. So let me turn on the steady rest so you can see what's happening here. See, the tool is hitting this. My steady rest doesn't have these things on it. The jaws only come out as far as this radius, so this won't happen, but this is the model that Esprit gave me for a steady rest, which is almost like mine. I need to remodel mine so that it's a little bit more accurate. You see it's kind of hitting these seals on the OD of the part and not closing all the way in this simulation. This steady rest actually opens and closes in the simulation in the beginning. So if I turn off the collision here, and then I can play this. And this is just a timing mark that they've put on the part that has to be milled in there, which I'm using one of my little ball end mills I had set up for the previous operation on the other end, the 16th inch ball mill. So that's the completed turn on everything here. You can see the whole machine and everything. That's a completed operation on this end of the part. And like I said, I just want to show that because I wanted to show the importance of the order of operations here, and why it's necessary to do things in a certain way. And I thought it might be interesting to see that. And it's kind of hard for me to show this in a video of the actual machine work because it's all happening inside and there's really nothing to show. You're just seeing this part spin in the steady rest. So I don't know if these kind of videos are interesting to people or not. Let me know in the comments.